Hello, my dear students. Welcome to this lecture series on real analysis with course code MMTC 202. So we are discussing outer measure generated by a measure, and in this lecture we continue this topic outer measure generated by a measure. So let us start with the following definition. Let x as mu be a measure space and a subset of x. A is said to be sigma finite. Here subset is sigma finite. If A can be written as if A is equal to union A n runs from 1 to infinity with measure of each A n is finite and A n is the other members of S. So clearly we can choose this sequence to be disjoint sequence, and that is already discussed. So next we have the following theorem. This theorem follows from previous theorem. In the previous lecture, the last theorem of the previous lecture, it's let x as mu be a major space, be a major space, and sigma be a semi such that as subset of sigma subset of lambda in the class of measurable sets, and let this is a major space, let x sigma nu be a major space. It's a major space, and let mu is equal to nu on S. Then by previous theorem, this mu star is equal to nu on sigma, but here we need to show that mu star is equal to nu of A, but this A is a sigma set in sigma, is a sigma set in this. That means A is a disjoint union of members of sigma. For every member A of sigma, mu star of A is equal to nu of A, but now you have to prove that this A to be a sigma, you have to choose this A to be a sigma set from this class sigma. That means A is equal to disjoint union of members of sigma, and you have to show that mu star of that disjoint union is equal to nu of the disjoint union. So it easily follows from previous theorem, because mu star of each an is equal to nu of an, and then you have to apply the additive probability. So you can easily prove this result. So I will leave this as an exercise for you. This next theorem, let x as mu be a major space, be a major space, x as mu be a major space if A is subset of x, then there exists a measurable set. A may be non-measurable. Non-measurable we can discuss next. The non-measurable set, they exist actually. A is a subset of x, then there exists a measurable set. A is any subset, but we can always find a measurable set E such that A is subset of E covers A, and and their outer measure are same. But their outer measures are same. For each subset A of x, we can always find a measurable set which covers A such that the outer measure of both the sets are same. So in particular, if this S is a sigma algebra, so in particular, if S is sigma algebra, it's not a similar but a sigma algebra, more strong. If it is a sigma algebra, then such a E is member of S. It's not only measurable but also the member of S, the sigma algebra. Okay, let's prove this result. So first, if it's infinite, if mu star of A is infinite, then which set I can choose, which is measurable, and the outer measure of that set is same as outer measure of A. So let's choose X actually. Choose X, which is measurable, and which contains X also, such that mu star of A is same as mu star of X by monotone property of mu star. Because mu star of A is infinite, therefore mu star of A is less or equal to mu star of X. Therefore mu star of X is also equal to infinity. So that means both are equal in that case. So now let's consider the case in that this mu star of A is finite. If it is finite, then we have to apply the definition of infimum here. If mu star of A is finite, now for each I, this I can be treated as epsilon 1 by I. Here. For each I, choose a sequence A and I in. So you can choose also disjoint sequence, but we don't need here disjoint sequence in S, such that A subset of union A and I, n runs from 1 to infinity, and summation n runs from 1 to infinity mu of A and I is less than mu star of A plus 1 by I. That's the property of infimum mu star A. Property of the infimum mu star of A. Mu star of A is the infimum actually. So and let's construct that set E, which is measurable. Let EI, it's equal to the union n runs from 1 to infinity A and I. Now what are A and I's? They are the members of S, therefore they are measurable. And we know that commutable union of measurable sets is measurable. Then AI is measurable for all I greater or equal to 1. And now let's take E to be intersection of EI's. So since each EI is measurable, therefore E is measurable. So that's the set E which is measurable. And in case if our S is sigma algebra, since A and I they are in S, so therefore their union, which is AI, it is also in S. Now each AI is in S, and intersection of members of SI is again a member of S, as S is a sigma algebra. So if S is sigma algebra, if S is a sigma algebra, then such a E belongs to S. So now we need to show that this E contains A, and mu star of A is same as mu star of E. So first we see it contains this it's actually A substop EI here. Now since A substop union n runs from 1 to infinity A and I, and union n runs from 1 to infinity A and I is equal to EI for all I greater or equal to 1. So therefore A is subset of the intersection of EI's because it is subset of each EI which is equal to E. So E contains A and it's a measurable set. So next we show that the outer measure of A is same as outer measure of E. Outer measure of E. Now outer measure of A, it's obviously less or equal to outer measure of E, and outer measure of E is less or equal to outer measure of EI because E is the intersection of EI, so that means E is subset of EI. And outer measure of EI, what's EI? It is a union. It's mu star of union A and I runs it's n runs from 1 to infinity, and that's less or equal to summation n runs from 1 to infinity mu of A and I because it's sigma sub additive mu star, and here I can replace mu star by mu because mu star is an extension of mu. Now this one, it's less than mu star of A plus 1 by I. Now letting I approach to infinity, we get mu star of A is equal to mu star of P because it's mu star of A less or equal to mu star of P, which is less or equal to mu star of A. Therefore mu star of E less or equal to mu star of E, mu star of A less or equal to mu star of E, which is less or equal to mu star of A. So that proves the equality. Mu star of A is equal to mu star of E. So this proves this theorem completely. So next we have a note. If X has mu is a measure space and if A is subset of X and E is a measurable set such that A is subset of X and A is subset of E and mu star of A is same as mu star of E. If given a measure space X as mu, if A is subset of X, E is measurable set A is subset of E, such that A is subset of E, and mu star of A is equal to mu star of E, then we say that E is a measurable cover of A. Then we say E is a measurable cover of A. So measurable cover always exists by previous theorem. It always exists. So next we give some examples of non-measurable sets, the sets which are not measurable. So you can construct a number of examples. Abstract examples you can construct, but there is one real example that's the subset of closed interval 0, 1, which is not Lebesgue measurable. First we give an abstract example of existence of non-measurable set. Existence of non-measurable set. So let X be equal to 1, 2, 3 and S be equal to 5 singleton 1, then it's not singleton 1, it's singleton 3, and then there is double 1 2, and finally we have 4 space x. Then you can easily verify that. Then one can easily verify that. Then one can easily verify that. S is a sigma algebra. S is sigma algebra. Sigma algebra means which is closed. Sigma algebra, which is closed with respect to union and complementation. That's there because complement of 3 is 1, 2, complement of 1, 2 is 3. So it's a sigma algebra. Now let's define a set function. Define mu from s to 0 to infinity by mu of phi equal to 0. That property should be there. And mu of 3, it's the same as mu of 1 2, which is equal to 1, and mu of whole space equal to 2. So you can easily verify that mu is a major. Then mu is a major. Now we find we show that mu star of the set singleton 1 is not because it's not a member of that sigma algebra, is not measurable. Because every member of S is measurable. So here it's not a member of S. So we'll show that this set is not measurable. So there are some sets outside of this class which may be measurable, but here we will show that this set is not in this class S, and we'll show that it's not measurable. It's not measurable. So for this, we first calculate the outer measure of certain sets. Then we use that. So now we calculate outer measure of 1 first. So outer measure of 1 is the infimum over all the covers, and you can see that it's equal to 1. Outer measure of the set 2 set, you can see it's also equal to 1, and outer measure of this doubleton 1 2, and you can see it's also equal to 1, because you have to take the infimum over all the covers of those sets 1 2 and 1 2. So they are all equal to 1. You can see, you can easily verify it. You have to choose the cover from S. So now you can see, if I set let A be equal to 1 2, then mu star of A intersection singleton 1 plus mu star of A intersection singleton 1 complement, and you can see these both are equal to 1. It's 1 plus 1, which is equal to 2, and mu star of A is 1 2, it's 1. So that means mu star of 1 is not equal to mu star of A intersection 1 plus mu star of A intersection 1 complement. So that means this one is not measurable, because for measurability, mu star of A should be equal to mu star of A intersection 1 plus mu star of A intersection 1 complement. So this implies singleton 1 is not measurable. It's not measurable. It's not measurable. So this one was trivial example. So you can construct a number of such examples. Next example is very important, but before proving that the existence of non-Lebesgue measurable set, we first prove the following lemma, which we are going to use there. So what's that lemma? It's lemma is following existence of non-measurable sets. This is done, and so we put the first following lemma. Let's prove this lemma. So consider we show that a subset A of R is Lebesgue measurable, is Lebesgue measurable if and only if X plus A, which the set X plus A belongs to A, is Lebesgue measurable.